Welcome to Plutus IAS. So today we are going to proof of a theorem. So we will see the proof. That means every to prove that every field is an integral domain. This theorem is also PYQ of UPSC. So also PYQ. It's an important theorem. We have to show that every field is an integral domain. So what the mean? Actually, we have to show that field imply that integral domain, and we'll also see that converse is not necessarily true. So first, okay, what the field actually? What the field? Any structure, suppose f dot plus this algebraic structure. When this is a field, you know that if f is a commutative, f plus is commutative, f star, that means non-zero element of f forms a commutative ring with respect to multiplication and distributive law holds. With these conditions, f be a field. So any field, that means field is actually what? With plus abelian group, f star, that means non-zero elements of f also form a group with respect to multiplication and distributive law hold. Now what is the integral domain actually? Integral domain is a commutative ring with unit element. Okay, so what is the integral of commutative ring with unit element and ring without divisor and ring without zero divisor. Okay, what the mean of ring without zero divisor? If R is any ring without zero divisor, then AB, whenever the A dot B equal to 0 in R, then imply that either A equal to 0 or B equal to 0. Any ring without zero divisor means what? Whenever A dot B equal to 0, that means AB belongs to R. AB belongs to R such that the A dot B equal to 0, then either A equal to 0 or B equal to 0. All the rings are not the ring without 0. For example, we know that the Z4, like the take the Z6. Z6 is a ring, but here the two non-zero element gives the equal to product is equal to the 0. That means this ring is not a ring without zero divisor, but now take the, this is also a ring. Set of rational number also forms a ring, or any two rational number if equal to product of any two rational number equal to 0 means at least one of them is sure 0. So this is a ring without zero divisor. So simple, what the mean of ring without divisor, without zero divisor means we know that whenever AB belongs to R such that the A dot B equal to 0, then either A equal to 0 or B equal to 0. So overall, what is integral domain? A commutative ring with unit element, and this ring is without zero divisor, then this becomes a integral domain. And what is the field? Field means also a ring. Field is also a ring, but yes, in a field all the 11 12 properties hold. Means with plus, means a field is always what? We can say that if F is a field, then obviously we can say that the field is a commutative ring with unit element. Okay, field is a commutative ring with unit element, sure. So what is remain? If you take the F as a field and you have to be show that F is also integral domain, then what is remain to show that actually it is only remain to show that this is a ring without zero divisor. So now, so we'll see the proof. So proof. So if you take, let F plus dot be a field. We shall show that F is an integral domain. We shall show that F is an integral domain. Or since field is what? Since field is a commutative ring having unit element, therefore in order to show that f is integral domain, it is only remain to show that remain to show that f is a ring without zero divisors. Okay, every field is a commutative ring with unit element. As we know that the field satisfy all the properties of a ring also. So field is a commutative ring having unit element, and therefore in order to show that f is, that means field is an integral domain. What is remain to show that more? That means f is a ring without zero divisor. So to be integral domain, ring must be what? Commutative, having unit element and ring without zero divisor. As field is a commutative ring with unit element, so in order to show that f is integral domain, it is only remain to show that f is also a ring without zero divisor. What the mean of ring without zero divisor? If any ring is a ring without zero divisor, then whenever we take any two elements of R such that a dot b equal to 0, then either a equal to 0 or b equal to 0, then actually we have to show this one. So for let a not equal to 0 and b belongs to f such that take any two elements such that a dot b equal to 0. We have taken a not equal to 0, and if f is a ring without zero divisor, then obviously we must have b equal to 0. If p is also non-zero, then f will be failed to be a ring without zero divisor, and f will never be an integral domain. But yes, we are taking the a and b two elements such that a dot b equal to 0, where a is a non-zero element. So since a not equal to 0 belongs to f, imply that a inverse belongs to f. As f is a field, and every non-zero element has the inverse element in field f. Therefore, just multiply by a inverse here from both sides. Therefore, a inverse a dot b equal to a inverse dot 0, and that implies that a inverse by associative law in field equal to 0, and that implies that unit element 1 into b equal to 0, that implies that b equal to 0. So we have b equal to 0. That means whenever a b belongs to f such that a dot b equal to 0, and if a is not 0, then we are getting b equal to 0. Similarly, we can show that by similar argument, we can show that b dot a equal to 0 imply that b equal to 0, and thus f is a ring without zero divisor. So f satisfies all the condition of integral domain. That means f is a commutative ring having unit element, and also f is a ring without zero divisor. Hence, f is a field, and therefore f is an integral domain. F is an integral domain. Okay, therefore every field is an integral domain. So we have proved that every field is an integral domain, but converse is not necessarily true. That means, okay, field imply that integral domain, but converse is not necessarily true. That means we have a example of integral domain which are not field. For example, set of integers this is an integral domain, is an integral domain, but it is not a field. It is not a field. So converse is not necessarily true. Maybe true also. Obviously, we have a example like the ZP. ZP, that this is a ZP. Okay, is a finite integral domain, is also a field. So yeah, but in general, converse is not necessarily true. So every field is an integral domain, but integral domain may or may not be a field. For example, here Z, we know that this is the integral domain, the ring, commutative ring having unit element 1 and also ring without zero divisor. That means Z is an integral domain, but this is not a field. Why? We know that the every non-zero element, that means for example, as 2 belongs to Z, but 2 has no inverse element in Z. We cannot get any element such that in a Z such that multiplication of this equal to 1. So there is no inverse element of 2 in Z. Similarly, for any element except 1 and minus 1, there is no inverse element of for any other elements. That means Z is not a field. So we will see in next video, that means every finite integral domain is a field.